Alright, so as mentioned at the end of the last video, we're going to look at now what happens when the fluids actually begin to move, right? So yes, in Pascal's principle, technically they are moving, but you have to understand it's confined in a system where now we're going to say okay, now it's free to flow and move and everything like that. And so the first thing is to look at is something called flow rate. So flow rate Q is defined to be the volume of a fluid passing by some location through an area. Sometimes they'll call this flux, and you do have to be careful when you say that word. It's all the same thing, right? There's all kinds of different flux that are in physics. There's electric flux, magnetic flux. There's this liquid flux, or fluid flux. And so the flow rate looks like a K. It's rate, right? Is just simply V over T. So I have a volume of a liquid or a fluid passing through a certain area for a given amount of time. So V is the volume, right, and T is the time of flow. And so if I had like a tube and I had like a sensor, right, and this fluid's passing through, and the sensor's like, okay, in 1 second, right, there's 5 cubic meters flowing through there, then I would have a flow rate of 5 cubic meters per second. Okay, and so that's what flow rate means. Okay, so this is how many this example is how many cubic meters of blood does the heart pump in a 75-year lifetime, assuming the average flow rate is 5 liters per minute. And so first thing we need to do is, okay, we need to convert this to cubic meters per minute, right? And so we're going to say 5 liters, so 1 cubic meter is 1,000 liters, and so that's going to be 5.0 times 10 to the negative 3 cubic meters per minute. And I'm going to leave it in minutes because I can do 75 years in minutes, right? So there's 365 days in 1 year. There's 24 hours in 1 day, right? And then there's 60 minutes in 1 hour. And I apologize for this being very sloppy. And so that's going to be 3.94 times 10 to the 7th minutes in 75 years, okay? And so all now I'm going to do is just simply use my equation, right? So I'm going to use Q equals V over T and say volume equals QT, right? And so I'm going to do 5.0 times 10 to the negative 3 times 3.94 times 10 to the 7th, and I'm going to get a volume of 1.97 times 10 to the 5th cubic meters. And again, I apologize just for being very sloppy. Okay, so that is the amount of volume that flows through the body in 75 years. Okay, now flow rate and velocity or speed, they're actually related as well, right? But quite different physical quantities. So if you think about water, the greater the velocity of water, the greater the flow rate of the river. Okay, the equation for flow rate related to velocity can be written as Q equals AV, right? And so A is the cross-sectional area in which it is flowing, right? V is the speed of the fluid, right? Now, because fluids are incompressible, again, so not really fluids, but liquids, right? So it's because fluids are really liquids are incompressible, the same amount of fluid must flow past any point in the tube in a given time to ensure the continuity of flow. When the cross-sectional area of the pipe decreases, the velocity of the fluid increases, but the volume flow rate does not change. So we say that Q1 equals Q2, right? Or A1 V1 equals A2 V2. And this is what we know as the continuity equation. So basically, if I have a pipe, right, that has two sections of area 1 and area 2, and I have three, right, let's say, units going through. I have 3 units going through here, okay? For this all to kind of match up, it has to move faster in area 2, right, than in area 1, because it can. Okay, the way to think about this, the easy way to explain this that students would understand is if I took a hose of water, right, and I just turned on the water and it just kind of spews out, right? It just comes out. But the second I decrease the area in which it's able to flow by putting my thumb over it, it comes shooting out faster. So think about that. That's what we're talking about here, okay? So here is an example with that. So you have a nozzle with a radius of 0.250 centimeters attached to a garden hose with a radius of 0.90 centimeters. The flow rate through the hose and nozzle is 0.500 liters per second, right? That doesn't change. Calculate the speed of the water in the hose and in the nozzle. Okay, so I'm going to do the first thing. I'm going to do it in the hose. Right, so Q is AV. So a hose has a circular cross-sectional area. So the velocity is going to be Q over the area of the hose, right? So the velocity of the hose is going to be Q, which doesn't change. Now, one thing I do have to do is I have to convert my flow rate from liters to cubic meters. So it's going to be 0.500 liters per second. We know there's in 1 cubic meter, there's 1,000 liters. And so that means there's going to be 5 times 10 to the negative 4th cubic meters per second. So it's going to be 5.0 times 10 to the negative 4th divided by pi times 0.900 squared. And it's going to tell me I have a speed of 1.96 meters per second. Right, so that's in the hose. So it's just spewing out, right? So if this is my hose, this is where the water just kind of like spews out, right? Now I'm going to put the nozzle on it. I'm going to have a smaller area, and that water is going to come firing out of there, right? And so think about that, okay? So now I'm going to use the same equation, but now I'm going to do it with the nozzle. Right, so it's going to be Q, 5.0 times 10 to the negative 4th, over pi times 0.250. Oh, sorry, I need to convert these. That's my fault. The number's right. I have it written down. I just got to convert. This actually needs to be 0.900 times 10 to the negative 2 squared. So this needs to be 0.250 times 10 to the negative 2 squared, right? And so that's going to end up being a speed of 25.5 meters per second. So you can see the speed in the nozzle is much greater than the speed in the hose. Okay. Now let's look at capillaries, right? And so one thing that you can do here with the equation also is, okay, I have the number, right? The total flow rate is the total number of capillaries or so forth times AV. All right, so the aorta is the principal blood vessel through which blood leaves the heart in order to circulate around the body. Calculate the average speed of the blood in the aorta if the flow rate is 5 liters per minute. The radius of the aorta is 100 millimeters. Okay, yes. And so the blood also flows through smaller blood vessels known as capillaries. When the rate of the blood flow in the aorta is 5 liters per minute, the speed of the blood in the capillaries is about 0.33 millimeters per second. Given I think one of the numbers is wrong. Oh, this should be 10 millimeters, not 100 millimeters. Sorry. Um, given the average diameter of the capillary is 8 micrometers, calculate the number of capillaries in the blood circulatory system, right? And so that's where we're going to use that NAV. So the first thing we do need to do is convert. So 5 liters per minute, we need to put that into cubic meters per second. So again, 1 cubic meter is 1,000 liters. In 1 minute, there's 60 seconds, so our flow rate is going to be 8.3 times 10 to the negative 3 cubic meters per second. So we can find the speed in the aorta, so it's going to be Q over A, and so it's going to be 8.7 times 10 to the negative 3 divided by pi times 10 to the negative 3. Sorry, times 10 times 10 to the negative 3. There's a lot of 10s running around there. Okay. Squared, and so the speed in the aorta, 0.27 meters per second. Okay, and so now what we're going to do is we're going to use that same equation. So we're going to use N1 A1 V1 equals N2 A2 V2, where we're going to say 1 is the aorta, right? 2 is the capillaries. Now here's the thing, you only have one aorta, right? And so we're going to solve this for N2. So it's going to be N2 equals N1 A1 V1 over A2 V2. So you only have one aorta, right? And so we know that it's going to be pi times 10 to the negative 3, okay? Sorry, the stylus is kind of messing up a little bit, right? Squared times 0.27. Although we know it's just going to be the 5 times 10, or 8.3 times 10 to the negative 3. Okay, and so the area, so pi times 4.0 times 10 to the negative 6 squared, because it tells us the diameter of a capillary is 8.0 micrometers. Okay, and it's moving at 0.33 times 10 to the negative 3 meters per second. And so we plug that all into our calculator, and we find that there's 5.11 times 10 to the 9th capillaries. Right, so there's 5 billion capillaries in the human body. Okay. Now, in the last video for this unit, we're going to look at Bernoulli's equation, which again still talks about fluid flow, and it really is just a restatement of conservation of energy.